Disasters are something that we humans have always been afraid of. Hurricanes, earthquakes, cyclones are all words that spark fear in our minds even today. Disasters cause large scale harm to life and are extremely difficult to deal with. With modern technology, response times have been lessened considerably. But one of the biggest challenges after a disaster is the immediate distribution of emergency services, allocating ambulances, paramedics, fire trucks, or even people to control the panicking public like the police. We propose a way to represent this problem in a way that it becomes an optimization problem that can be easily subjected to meta-heuristic algorithms. To do this, we first created objects of various entities in the situation, including the site of emergency, the service location from where the emergency unit would be deployed, the units that would finally deal with the problem, and finally, the distribution of the units. The way to solve this problem would then be to optimally allocate units from each service location to the designated emergency site. Now this becomes something familiar. This fits the skeleton of a combinatorial optimization problem, and this is where we can bring in meta-heuristics. To formulate this problem, mainly the fitness function, we need to first determine what factors would determine how good or how bad a particular distribution is. The distance is one of the most important factors here. We obviously cannot allocate an ambulance that is currently in a hospital multiple kilometers away where we have another one close by. The second factor here is the severity of the emergency situation. Taking an example of an ambulance, there are multiple types, some with multiple beds, more facilities, and some equipped with just the bare essentials to transport the person to the hospital. By integrating these two factors, we get the equation for the fitness function. The problem is not yet complete. This equation is also subjected to a few constraints. First, the most obvious one is that an ambulance cannot be allocated as the primary unit to a fire emergency. We need a fire truck for this. The second is that we need to have some units in reserve. The proposed approach takes the situation at one possible time and determines the optimal solution to this. We need to have an appropriate number of units in reserve for any emergency that comes after the specific moment. To do this, we take the number of high severity emergencies to calculate the threshold limit for the minimum number of units to be kept in reserve. We also need to do a reality check here. The number of units allocated cannot be less than the total number of available units. Now, since this problem is a combinatorial optimization problem, we need to add one more layer to before any meta-heuristic can be used here. This is because we need to convert this discrete problem into a continuous one. This layer here is the SPV rule. To test this, we have implemented the particle swarm optimization algorithm. With the SPV rule, PSO tries to give us an optimum solution by iterating over some randomly generated solutions and getting better with time. This clip over here shows how PSO comes to a solution in a span of 100 iterations with 15 emergencies inside a square region of site 200 units. This approach to formulating a post-disaster scenario emergency allocation can be used to dynamically allocate units to deal with and control the effect of disaster on human lives. This model of disaster resource allocation can be expanded further to fit real-life situations and can be solved using various optimization algorithms.